Hello everyone. In one of the previous videos, I had mentioned that once we have this equation and once we have the value for p, then we can find out from this particular equation, although it involves this complicated looking thing, the value of k such that this equation is satisfied. Because you note, and I again emphasize here that the only thing which is not known in this equation once a value of p is given to us is the value of this k, and once we know the value of k, we'll have the knowledge about this alpha, because k is equal to sine alpha by 2. Okay, now because this is such a complicated looking thing, but I had mentioned this also earlier, that despite its look, it is a very special kind of thing which appears a number of times in different fields. So this particular integral, it is referred to as the elliptical integral of the first kind, and it is actually available as a built-in function within symbolic Python. So we are going to utilize that to see how we can find out the value of this unknown k. All right, so on to Jupyter Notebook now. Okay, so the first thing that we are going to do is import NumPy. Okay, and I'll also import from the scientific Python package. So this SciPy, SCIPY, this is it stands for scientific Python, and within it there is this special package which contains this pre-built functions. So what I'll do is I'll import it in a slightly different fashion, because this contains a huge number of special built-in functions. I don't need all of them. I will just import only the one that I need, and that is this elliptical integral. Okay, so from scipy.special import ellipk. That should do the job. Okay, all right, so now that we have this, what we are again going to do is we are not going to separately specify a value for this p and then these different values of e, I, and l. Rather, what we'll do is we'll specify a value for this particular ratio, p by p Euler. Okay, that should be sufficient. So that is basically equivalent to specifying a value of p if the values of e, I, and l are also known to us. Okay, so it'll work in that fashion when we have to deal with fewer number of parameters. So we set this up, p by pe. Let's say we put this as 1.1. Okay, I mean, we can play around with different values, but just for the sake of concretizing our process, we'll just set it up as, this is just an arbitrary value. Okay, we might as well take this as 0.85 and test out various things, 1.5 to anything. All right, now what we want to do is, see, our job here, okay, our job here is basically to find out a root of this equation, where when I say root, I basically mean the unknown value of this k. Okay, so can I not think of this equation in a slightly different way, that this minus this term is equal to 0. So if I just write it like this. Okay, so whatever is present here, that I keep as it is. So p by p Euler, just transposing this entire thing to the left hand side. Just this small change, but what I'm going to say is that this entire left hand side is some function. Okay, it is some function of k. Now my job basically reduces to finding a value of k such that that function value is equal to 0. Now let's see how we can actually implement this idea in symbolic Python. Okay, so the first thing that we are going to do is define a function. So we can give it any arbitrary name. So we'll just call it Elastica function. So the only parameter which it will take as input is the value k. So for different values of k, it is going to give me different values. Okay, so I want to set this thing up square root of uh, p by p Euler. Okay, minus 2 by pi, so that will be written as 2 by np dot pi multiplied by this entire thing. Okay, this entire integration, but I don't have to write out that entire thing because that entire thing, that integral itself, is captured by this elliptical k. Okay, so all right, so that's all there is to it actually. So let's just check if this thing is set up all right. So what I'll do is, just as a test, I will input some value of this k. Now our immediate question is, if we don't know the value of k, what value should we input? So a priori we do not know what this value is, so but we do know that k is equal to sine alpha by 2, as I've already written down here. As you can see, this k is equal to sine alpha by 2. Now because of this particular form, you can be confident that no matter what k is, it should always be lying between 0 and 1. Okay, it cannot be more appropriately, it should be lying between -1 and 1. It cannot be anything beyond that. Okay, so just as a test case, okay, just as a test case to see if we are getting some value, okay, it's always good to check that. Let's just do this. Okay, it is giving us some value. At least it is not anything like minus infinity or not a number. Okay, so you should always check these kinds of things. Okay, now suppose we do give this as some value greater than 1. Let's say we give it 2. Okay, now you see that this is not a number, because of course, I mean, k is defined in such a fashion, and this elliptical integral is also built up in such a fashion that, I mean, this is a non-admissible value. Okay, so we'll just keep it like this. Okay, now all that is fine, but how does setting this up help us in actually implementing the process of finding out the unknown value of k? Okay, these are just test values that I was taking, 0.2, 0.5, whatever. Okay, but we have to find out the value. Okay, so our job basically reduces to this, that we are going to input different values for this at this place, for this Elastica fun input parameter, such that this Elastica fun turns out to be 0. So this value that we are getting, this value should be as close to 0 as possible. Okay, so suppose we take this as like this. Okay, suppose we take this as some minus value. Let's see what happens there. So you see it has become positive now. Maybe I decrease it like that, so it is still positive. If I go like that, so you see this is a completely hit and trial kind of method. I don't know what is going to happen. So just to get an idea, okay, just to get an idea of the behavior of this Elastica function, the kind of values that it takes, perhaps it's not such a bad idea to plot it out. Okay, we are going to go forward and actually find the root of it properly, but before that, it would be informative if we can actually get some kind of a visual depiction of the values that it is taking. So towards that end, what we are going to do is we are going to supply to it a range of values for this k. Okay, so let's say we supply to it this range of values. Let's say like that. So where 0 is the lower limit of this range, 1 is the upper limit of this range, and the 0.01, it stands for the increments within this. I could easily take 0.001, that is only going to increase the number of values of this k values variable. Okay, so I have that. Now what I would like to do is to investigate the various values of this function corresponding to each of these values stored within the k values variable. So if I do that, you see I do get an array of values. Okay, so this entire set of values that I obtain, it corresponds to each of these values of k, of the k values variable, going from 0 to 1 with increments of 0.01. Now I do have the data now. All that I have to do is to plot it out. Okay, so for that we are going to use matplotlib. So let me do that a little bit systematically. I'll use this input cell itself. So I use this line such that all the plots are generated within this Jupyter notebook itself and not as a separate figure. So that will keep things nice and tight. But I do have to make some appropriate imports. So this is the standard way we import the plotting facility that is built into matplotlib package. So this is matplotlib.pyplot, something like PythonPlot. That is usually within the Python community imported as PLT. So I mean, just like we had done this kind of an import earlier, import numpy as np, which is kind of the idiomatic behavior of people using Python. So also this is the idiomatic behavior. I mean, you can use anything else. You might as well say import matplotlib.pyplot as tiger, okay, or rabbit or elephant, doesn't matter. Okay, but this is just idiomatic behavior. All right. Next, what we are going to do, we want to plot on the x-axis, on our x-axis, this k values, and on the y-axis this value, okay, this Elastica function values. Now what we are going to say is that whatever the values we are getting of this function, that will call as a residual. So that is basically a term from numerical methods. So so any difference from 0, that is like a residual. So again, just a choice of a variable name, but we actually have to store those values properly. Okay, I mean, we could do something like this. Let's try this, try if this thing works. Sorry about that, I missed one bracket. Okay, so it works. I was going to show it to you in a slightly different fashion, a slightly lengthier fashion, but I mean, this is just an easy, straightforward way of showing you. So it works. Of course, please note that that when you actually go into a real project work, please do not leave your plots in this kind of a bare bones fashion. It is extremely unprofessional. I sincerely urge you to please present your plots and your figures in a nice professional way, where you take care of the size of your fonts here and here, and very importantly, that you never ever forget to write the label in the x-axis, the label in the y-axis. Okay, so instead of pontificating, let me just try to do that myself. Okay, so on the x-axis I have the k, and on the y-axis I have the residual. I'll just write that like that. But even this is not quite professional, although it is just satisfying the bare bones necessity. Okay, you should do better than that. Okay, in a real project work. Okay. So we have the values of this residual like this, and this k here like this. Please note that these values of the Elastica function that we are obtaining, this is corresponding to our choice of P by PE. Okay, this P Euler, this ratio, this particular ratio. Okay, that is very, very important to note. All right. Now, you see, what we are trying to get at here is that, okay, fine, we have obtained these values. Okay, and wherever this particular curve, it intersects uh, the x-axis. Okay, so our x-axis would be is a horizontal straight line passing through this. So let me see if I can just plot that out. Okay, so plot k values just for visual, so ease of visual understanding. So I'll just plot a series of zeros whose length will be equal to the length of the k values variable. Let's see if that works. Okay, that's it. So you see, this is a horizontal straight line passing through the 0, and wherever this plot it passes through this horizontal axis, it is somewhere, just from visual observation we can see that, or visual inspection we can see that it's somewhere here. Okay, a little bit this 0.2. Sorry about that little break. Okay, so as I was saying, our job basically boils down to actually finding out this particular root. Okay, so all this is just a rough way of estimating the value of the correct value of k. We understand that it should be somewhere close to the 0.2 value, but we really have to find out the exact value. So how can you do that? So what we'll use is we'll utilize the root finding capability within Python, and for that we'll again have to import something from this SciPy. So from SciPy, so this time we are going to use the optimize package, which has the root finding capability built into it. Okay, so from scipy.optimize import root, and then we have to supply to it the name of the function, and then we'll also have to supply to it a value which is an initial guess. Okay, so if you are if you're a little bit familiar with numerical methods, you will remember that sometimes for these initial methods we do for these numerical methods we have to provide an initial guess. So let's provide an initial guess as 0.3 maybe. Let's see what happens. Okay, so you see, it does give us something. Now this something is the actual solution. Now you see here that I mean it provides the solution in a slightly strange fashion, but the key thing to note here is this thing, the success true. Okay, the solution has converged, it's true, and the real answer that we are looking for, that is present within this x. Okay, so what we are going to do is we are going to write like this, or we can write it here itself. Solution is equal to root of this. Okay, now of course it doesn't write anything, but we can just display the solution again. We'll display that thing, and then we can extract from this solution structure, which is presented in this fashion, this x. Okay, and from that x we can go a little bit deeper and then extract out the actual value, this 0, and that will be the answer to our k. So that will be our k. Okay, all right, so our k solution is this, and let's just check for once if that is indeed true. So what we are doing is we have gone the other way around and now inputted the k solution answer that we have just found back into our Elastica fun, and let's see what it gives us. You see, this is nicely 0. That's what we wanted. Okay, so if we use this value of K solution corresponding to the choice of P by PE that we have started out with, we do get our answer. Okay, so what we were saying earlier that given a value of P or equivalently P by P Euler, our job is to find out the value of K such that this equation is satisfied. That job is done now. Okay, all right. Next, once we have the value of this K, what we are going to do is to try to find out the deflection W. Okay, so let's go back to our notes and take a look there what we have done. So we had covered the steps and then we had arrived at this particular expression for W. Okay, so this was present in just the previous video, and now you see our job is, I mean, almost done in the sense that we can just code it up. Okay, but there is a little bit of a problem in the sense that this ratio is still not in the form P by PE that we would very much like. Okay, so let's set it up like that, and you also note that this sine squared theta by 2 that can be again rewritten in terms of the phi. So let me just go to the new page, and I'll copy this thing out, go to the next page and just redo whatever I need. There may be a little bit of an adjustment over here just to make it look a little bit better. Okay, I think I'm happy there. All right, so you see I introduced this pi square EI. I also introduced this L square, so that what I'll be adjusting here is with this pi square, this P, and this L square. Okay, this term here will be K square minus, now you please note that earlier I had used this sine theta by 2 is equal to K sine phi. All right, so this thing is going to be K square sine square phi. All right, so what I'm basically getting here is that this is going to be twice L by pi. So this L is coming from this L square. So you please note that this is under the square root, and this pi square is coming out as this pi, and what I'll be left inside is this P Euler. So whatever was present in the numerator, that is pi square EI by L square, that was my P Euler, and I just have this P left, and this term is simply K square minus K square sine square phi. I think I should be writing that as the other phi, not as this phi. Okay, now you please note that although we have supplied in our code in Jupyter notebook this ratio P by P Euler, it's just the inverse of this, but we have not yet provided the value of this L. Okay, but not to worry, what we can do is we can normalize this this deflection, which is a length value, by this L. Okay, so we normalize or non-dimensionalize this W by L. So what we say is W tilde or W bar, maybe W bar is equal to W by L is equal to 2 by pi square root of 1 divided by P by P Euler. So I'm trying to write it in a fashion which will help me to directly code it up in Jupyter notebook. Okay, so this is what I'm going to write there. Okay, this W bar, basically I'm trying to plot not W but W bar. All right, let's see if we can do that. So the thing that I have to input here, you please note that before I go to the Jupyter notebook, that when this theta, it goes from it basically goes from alpha to minus alpha, or you can say that it goes from minus alpha to alpha, either way. So when it goes like that, then this phi, it goes from so let me write that down, that as theta goes from minus alpha to plus alpha, I should write that as the proper phi, of course. The phi goes from minus pi by 2 to pi by 2, and you can just check it here. Okay, so theta is equal to, I think I did this earlier, but anyway, I'll just do it quickly once more. So this is minus sine of minus alpha by 2 is minus sine alpha by 2, and this k itself is sine alpha by 2. So this is sine phi equal to minus 1. So phi is equal to minus pi by 2, and when theta is equal to alpha, I have sine alpha by 2 is equal to sine alpha by 2. Let me put a dividing mark over between these two. So sine phi is equal to 1, which implies phi is equal to pi by 2, which is exactly what I have written here. So when you have theta going from minus alpha to plus alpha, I have phi going from minus pi by 2 to pi by 2. So this basically supplies to me the range of values over which I should vary my phi, such that I obtain my value of w bar. Rest of the things are already known to me. I have just now found out the value of this k, and this p by p Euler I have already taken. So I know basically everything, I just need to plot it out. All right, let's do that. Okay, so phi, I'll put the range here, minus pi by 2 to pi by 2, and let's say I want to divide this entire range, which is basically pi. So as we go from minus pi by 2 to pi by 2, the entire range is pi, and that I will divide into 200 divisions. Okay, so let's say we set up our n as 200. I'm setting it out like this so that if we wish, we can later change n to maybe 500 or 1000, whatever we want, if we want finer refinements in our increments. All right, now correspondingly, I would also want the values of w. What I can do here is let me just take a look. So I want this particular form, right? So let me see if I can write that down directly, this w bar expression. So this should be 2 by pi square root of, let's try that. W bar is equal to 2 divided by pi times square root of 1 divided by p by pe, and then I have this part, square root of k square minus this, times square root of k square minus k square times sine phi, but that should also come with a square. Let's just check that. Right, k square minus k square sine square phi. I mean, I could have converted that into a cos. That would have been easier, but all right, I'll just keep it like this. Okay, that would have been far easier to write actually. I would have just ended up with k cos phi. Anyway, uh, I've already written it. So let's see if we can obtain this. So again, just like before, let's try this. Phi um, w bar. Let's see what it gives us. I think somewhere I may have missed. Yeah, NP. Okay, that's it. I'm getting my solution for W. Now, the first emotion that you have when you have such a plot is happiness, but then a certain almost a little bit of a negative feeling may creep up, in the sense that does this really mean that this kind of a deflection, if this is indeed the W, and please note that this is not even the W, this is the normalized W, so this is W divided by L. Does this deflection curve, does this really mean that the beam is deflecting in such a like a fantastic fashion? But no. Okay, so please be careful in noting the units here, okay, or the values here. So you look at the range here. This is minus 1.5 to 1.5, and this is going from 0 to 0.2. So this is a really small value. So in order to avoid any such illusion regarding the way in which it has and this deflection is shaping up, so you please you can try to set the aspect ratio of the axis as equal. Okay, now you see it's much better. Okay, so this is a little bit more physically intuitive. Of course, uh, once we have this code ready, whatever we wanted to achieve, we have achieved. But please note that we are working under this rather arbitrary choice p by pe equal to 1.1. Now, it is our hope that if we increase this, maybe you should be getting larger values of the deflections. So let's check that. So once you have the code ready, you should go into a scientific or a scientifically curious pursuit to get further insights into the actual physics of the problem. Okay, let's see. Of course, you should be careful in noting that you should be getting answers. Okay, I mean, okay, you see here the value of k. Even before you go into the actual root finding, you can see that it has considerably increased the value of this k solution. So maybe it's a good idea to help symbolic Python a little bit, to give it a value closer to what we can actually visually inspect from here. So it is again, success is true. So we do have a solution in our hand, and let's just check if it is indeed so. So earlier we had obtained a value of 0.0 that made us perfectly happy, but you see here this also should make us perfectly happy in the numerical method sense, because this is basically just 2 times 10 to the power minus 16, which for all intents and purposes is 0. Okay, so I think we are good here. And before I press shift enter in this cell which plots out the deflection, you please note that it's more or less in that 0.25 range. Let's see if that increases or decreases. Okay, it'll be interesting to see. So we don't see much of a change here. Sorry, I have made a mistake, I believe. Right, because the k is okay. What I should have done earlier also is to take a value of this k solution properly. Okay, so here this k should not be a k, should be a k solution. Okay, it should be a k solution. The value of k, if you look at the code, it was not even present. So you should be absolutely right in suspecting like what that something has gone wrong here, that why it was accepting, it was not even showing an error, that k solution that k was given and it was not even defined, why was it giving an answer even. So the issue is that just before I had started the video, I was just trying out a few things, and from that I had not restarted the kernel, and that is why that k value, that value of k had was already present in the environment. Okay, so let's do this now once more. You see that it has slightly increased. So what we can do is we can go back and change this to 1.1 and run the entire code again. So it is taking a little bit of time. You see it has gone back to the previous kind of solution, and we have this thing here. Okay, so this is actually less than 0.25, and if I just remove this thing, this equal, it'll be easier for us to actually look at the value. See, it's even less than 0.15. Okay, now I go back and change it to 1.5 and then rerun the entire thing. Let's see what it does now. You see it has increased considerably. Okay, previously for a value of p by p equal to 1.1, it was giving a value of the highest value of the deflection less than 0.15, and please note that this is the normalized value. I think I should apply the labels here. So plot x label, so this is phi, and the y label here is w bar. Oh, sorry, that's a spelling mistake there. Okay, so this bar is barely showing up. Let me just try to rewrite that. Okay, that's better. So this w bar value here is close to 0.3 for a value of p by p Euler 1.5, and just as a last check, there are a number of things you can test out here. I'll just rerun the code here. It only takes a few seconds. You see it has increased. Okay, now what I'll do is I'll reduce this value. Let's see what happens then. 0.5, and this time I'll not run all the cells together, rather I'll just run them one by one. So now you see this is rather curious. Okay, this is rather interesting. You see, when we plot this out in the admissible range of k from 0 to 1, then it is not cutting this horizontal axis passing through 0, which means that for the value of p by pe, p Euler has 0.5, that is what we have chosen here. So that's a relatively small value compared to the values that we were choosing earlier. We do not end up with any solution of k. This is basically what it is telling us. So what the interpretation of this result is that for a value of p by p Euler equal to 0.5, basically our beam does not buckle. Okay, that is the prediction of this theory. So it's really pointless to proceed after this for this value of p by pe equal to 0.5. Okay. Next, suppose we increase the value to, let's say, 0.9. What happens then? You see, it is almost touching this, but not quite. We still don't have a solution. So P by P Euler equal to 0.7, 0.9 doesn't also give us anything. What about 0.95? It's quite fun to actually do this thing. See, it's quite close, but not, no, it's still not touching it, still not crossing it. If we increase it to 1, okay, at the value of the P Euler, okay, so we may have a solution here, and let's see what happens if we actually try to run this. Okay, so it does say that it is success true, but you just note the value of the case solution it is generating. Okay, so it is practically 0. Okay, so for k solution equal to 0, that's what we are getting. And of course, I mean, if we run this, then also we are going to get this k solution, that's fine. But if we run this, you see the deflection that we're getting is of the order of 10 to the power minus 17. Okay, so that is basically 0. Okay, so if we had to actually uncomment this line and rerun this, this will look like a straight line. That's it. Okay, so even for a value of P Euler equal to 1, the more exact theory that we have found out involving this theta s coordinate system, that is telling us that there is barely any buckling here. Okay, but if you just increase it a little bit more, okay, as we were doing earlier, for a value of 1.1 or maybe even 1.05, okay, so now if we run it, you see there is a nice crossing of this line, of this horizontal line, and we do get a solution. Which is a non-negligible value. Okay, and this time we should be getting some visible buckling here. Okay, so there is a lot to explore once you have the code ready. So I believe this thing will encourage you to explore such situations on your own. Maybe you can change the boundary conditions a little bit and test out and rewrite the code and see what happens. Okay, so on that note, I will end this video. Thank you very much.